Hello, everyone, and thank you for joining. This talk is about landmarks and regions, a robust approach to data extraction. I am Suresh Parthasarthi, and this is joint work with my colleagues at Microsoft Research and PROS team in Microsoft. Extracting data from semi-structured documents is an important and pervasive problem which arises in many real-world situations. This can be extracting fields like name, booking ID, hotel name from a booking email in HTML format, or fields like insurer name, customer name, and amount from a scanned image of a receipt or an invoice. We call these documents collectively as form documents. These extractions power various downstream tasks like displaying a flight card as shown in this figure or automated payments in a finance workflow. While the term form documents is itself loosely defined, these documents share some common characteristics. They are often generated by software, and many documents are generated with the same format, which makes them amenable to programmatic data extraction. These documents come in heterogeneous formats and are continuously evolving with time. For instance, each airline follows a different format, and the same airline may change formats over a period of time. Hence, extracting data from these documents is not a one time task. The system needs to be robust to evolution and needs to be routinely updated and maintained. We would like to build a robust extraction system which can handle these heterogeneous formats at scale with minimal human intervention and be efficient at runtime. We proposed the Heterogeneous Data Extraction Framework or HDEF few years back. HDEF combines machine learning and program synthesis to solve this extraction problem. Let me give you a quick overview of what HDEF does. In HDEF, we use machine learning models for generalization and programs for predictability. To start with, we train a deep sequence model for this extraction task using some label data. The good thing about these models is they can generalize on unseen formats or unseen domains. Let's say the ML model predicts with 70% precision on a new format. We propose an algorithm called as noisy disjunctive synthesis or NDSyn to synthesize extraction wrappers automatically on top of these noisy labels. In effect, we use the ML model as a weak labeler and use synthesis block as a regularizer. We deployed HDF in multiple products at Microsoft. This one pertaining to email extraction is one of my favorite. HDF saves around 120 hours of flight model maintenance time or 50% of data annotator bandwidth. We deploy the synthesized programs at runtime. These are not only efficient but also can be debugged, tweaked, and redeployed if required. Based on our production experiences, we observed instances where the synthesized programs tend to overfit. The goal of this work is can we avoid or even reduce this overfitting? In the rest of this talk, I will just focus on the synthesis block over here. Consider this flight email. It is a HTML file, and we would like to synthesize an extraction program for flight departure time. Using NDSyn, this is the program which gets synthesized. Now let's dissect this program. This program has two parts, a CSS selector and a text program. The initial parts of the CSS selector narrow down the blocks to extract from. In this case, the air blocks. Within each block, it extracts the sixth last child, and within each child, it tries to extract the second child. All is good until this email shows up with an extra mail row. The extraction program breaks, and instead of outputting the departure time, it outputs the arrival time. Now, consider this email with a hotel block added. Instead of outputting the flight departure time, this program outputs the hotel checkout time. As we can see, this extraction program is brittle as we are trying to synthesize on this entire document, resulting in a complex program with many absolute indexes. We would like to do much better than this. We would like the extraction to focus only on the required regions and be robust to any changes happening outside these regions as well as to changes within these regions. The extraction program should be robust to region permutations and occurrences. And finally, we would like the program to be simpler than the one above. In this work, we focus on the following aspects. Before I delve into the technical details, let's try to locate McDonald's on this map. This does not seem to be an easy task, but if I were to tell you a landmark nearby, Liverpool Street Underground Station, this task becomes a whole lot easier. This is also a natural way humans navigate documents and layouts. Now, can this intuition carry forward to documents? Now, using this idea, let's try to extract departure time from this HTML file. The phrase depart over here is a potential landmark which can be used to locate the value of departure times. Using these landmarks, we can narrow down the regions we are interested in. Now, this problem is a lot easier than extracting from the entire document. In the final step, we can extract the required field values from these smaller regions. We express the extraction task as a quadruple consisting of a landmark, region program, a blueprint, and a value program. Note that the CSS selector over here is much simpler than the one I showed you before. I will talk about each of these components in detail in the next few slides. This brings us to the key idea. Using landmarks allows us to decompose the field extraction problem into two subproblems, region extraction and value extraction. Region extraction takes the document as input and produces a small region as output guided by the landmark. Value extraction takes the small region produced as in the first step as input and extracts the desired field values from the region. Based on the clusters, we can infer the landmarks, which in turn induces regions which lead to clusters. As there is a circular dependence between landmarks and clusters, we infer them jointly. In this talk, I am going to talk about landmark-based robust synthesis and answer some of these questions. What are these landmarks, regions, and blueprints, and how do we even infer them? How do we synthesize region programs and value programs? I will not go into the details of the clustering algorithm. More details can be found in our paper. Let's start with landmarks, regions, and blueprints in the case of HTML. Here, the field in consideration are the flight departure times marked in blue. Landmarks are a form of data invariance present in all documents of a given format and occur near to the fields of interest. In this example, depart string over here is a potential landmark for extracting the departure times. Given training documents from a document cluster, we can easily infer these landmarks with a scoring function which factors in the closeness to the field value and the size of the region it induces. A region of a document is a set of contiguous locations. A region can be thought of as a subdocument. We are particularly interested in regions which enclose the field values and the landmarks. We call these regions as regions of interest. A blueprint is a hash of the region. Blueprints are used in clustering and during inference. In the case of HTML, we can compute these blueprints easily using the tag structure. In this case, the blueprint happens to be /3d. Now, let's look at how do we synthesize region programs for HTML for a given cluster. The input to this stage consists of a landmark and the field values for each training document in the cluster. For HTML, we can express the region program in terms of the number of parent hops and sibling hops. That is, starting from the landmark node, traverse up parent hops times and traverse to the sibling hops time. In this example, a parent hop of 0 and a sibling hop of 1 gets us the green region. The single sibling hop over here implies that across all the training data, the extraction value lies one sibling away from the landmark within the same parent node in the DOM. The parent hops and the sibling hops are computed based on all the annotated training documents in the given cluster and hence produce a large enough ROI that includes the location of all the field values we want to extract. This is the overall system. We start with the training documents and we infer landmark and cluster jointly for a given field. For each cluster, we synthesize a region program and an extraction program. These are the steps during inference time. We perform inference per cluster. We start by locating the landmark. We use a simple grep for this, which makes it inherently inexpensive. Now, using this landmark and the region program, we narrow down the regions to extract from. Then we compute a blueprint of these regions and match it to what we learned during training time. If the blueprints match, then we run the synthesized value program on the given region to get the required field values. We can also follow the same procedure for scanned images. For images to start with, we perform an OCR to get the text and the corresponding bounding boxes. Landmarks and regions in images are similar to the HTML case. Landmark regions are shown in orange over here, and region of interest are marked in green. In HTML, owing to the explicit tag structure, we could compute a region blueprint easily. In images, this is much more nuanced. We express the blueprint of a region in images using what we call as the box summary, which consists of the neighborhood information for a given box and the frequent n-grams. For instance, the box summary of engine number over here can be computed as follows. There is no nearby box on the top. To the left, we have the chassis number box, which happens to be a frequent n-gram. To the right, we have the registration date box, which also happens to be a frequent n-gram. To the bottom of this engine number box, we have a specific value. And since it's specific value, we denote it by an existence of the box. Now, let's look at how do we synthesize region programs in case of images. We create a visual DSL which operates on top of OCR boxes to synthesize the region program. Intuitively, we traverse aligned OCR boxes in an absolute or relative manner. For instance, to extract out the chassis value over here, we start with this chassis number landmark and we come down and we extend right till we hit a pattern with 13 digits. Or if this engine value were to be absent, we would like to go all the way right till we hit the registration date value. We synthesize a disjunctive region program in case of form images as shown by these two programs. Now, once we have the regions, we use Prose library to synthesize the extraction programs. In case of HTML, we use a combination of structure and text programs. And in case of images, we concatenate all the text in the region and use the text program for extraction. Let's look at some of the results of landmark-based robust synthesis. In the HTML scenario shown in the left, we perform our experiments on a machine-to-human email dataset, which consists of anonymized flight reservation emails. We perform our experiments in two settings. A contemporary setting, where both the train and test data are from the same time period, and a longitudinal setting, where the test data was collected several months after the training data, allowing for new formats to organically enter the dataset. As seen from these numbers, LRSyn is robust to the new formats coming into the dataset. Also, the programs synthesized by LRSyn have only 2.95 selectors as compared to 8.51 for NDSyn. This signifies that the programs learned by LRSyn are way simpler than the ones learned by NDSyn. Also, this confirms to our inherent assumption that the landmark strings and the regions around them do not change as often as the overall format. In case of images shown on the right side, we perform our experiments on two datasets. The M2H email dataset in the longitudinal setting converted as images, and an internal finance dataset which consists of scans of receipts and invoices. We compare ourselves with Azure Form Recognizer, which is a state-of-art neural model offering by Microsoft. We use 10 training instances to train a custom model in AFR and use the same set of documents to synthesize the programs. For the M2H dataset, we see that LRSyn performs much better than AFR. And even on the finance dataset, we are having LRSyn which does better than AFR. In summary, we introduce the concept of landmarks and regions in program synthesis, resulting in robust and simpler programs. We have very promising results in HTML and images scenario, and we have ongoing deployments in multiple products at Microsoft. As a natural progression, we are exploring ways of combining machine learning and landmark-based robust synthesis. And that's my talk, and I'm happy to take any questions.
Thank you so much for the great talk. So it looks like we have a question on Slack, so I'll go ahead and read that. Many sites implement obfuscation on their generated HTML. For example, Facebook changes the class name of elements and splits a text field into multiple elements. How would LRSyn handle such scenarios? And that's from Mingzhe.
Yeah, that's a very good question. So we tune the expressivity right in our DSL right, on the things we hook onto right while synthesizing a program. For instance, like we don't want to hook onto certain class names, right? For instance, right, and we would like we also synthesize a disjunctive program, right? For example, like I can say that come to this landmark, right, and from this go 3 parents down, right? And like check for a field value which looks like a date, right? Or like something, right? Likewise, I can say that, okay, like there can be clusters where like this one, the descendants look something different, right? But over time, like what we can do now is like, so we have the ML model outputs and we have the program outputs. And if they differ, we like kick off this resynthesis loop, right, again, and we get new programs, right? If, for example, we have seen like cases where Amazon also changes like these class names very often, right? So we resynthesize these programs and we can deploy them automatically, right? Yeah, that's a great question, right? And we do handle them in production systems.
Right. Yeah, that's really cool. So if you're not hooking onto class names, you're just hooking onto the hierarchical structure of the DOM?
Yes, that's correct. Yeah.
Cool. Have you, I'm just curious, have you compared like the same document in OCR versus in HTML and the performance of that, or is that not something that's
for the images part, right, we do this experiment where we convert the HTML to images, right? And we perform the experiments in images, right? Right, for cases like HTML, the OCR is very clean, right? And we get improved performance in images because these nuances of these tags and like these hierarchies don't exist in images, right? So you just come down and like go right. So we do observe a bump, right, when we treat them in a visual way. And also in images, for example, receipts and invoices, right? Like sometimes these images are not as clear, like as a HTML to image, right? Where we again see like there's an improvement, right, with our technique where we narrow down on a smaller region, right? But in many cases, right, to answer your question, right, like product teams prefer like working in HTML, right? For example, if you are in a browser, right, you don't want to take a snapshot of that region and like do a visual DSL on top of that. Instead, many teams like prefer CSS selectors, right? Which is why like we work in both of these worlds, right? HTML world as well as the visual world.
Got it. That makes a lot of sense. We have another question, which is, how do you deal with the case when there's no clear landmarks?
Right. Currently, we don't handle these cases. Right. But as a natural progression, like to where we are going, we want ML model, right? Like to take some of these responsibilities, right? Like so one can imagine like even a generalization of the concept of a landmark, right? A landmark need not be a specific text, right, found on the page. Instead, it can be like a semantic representation of like various text forms, right? Or even images, right? Even the region finding can be outsourced to a deep model, right? Where the deep model can say that, oh, this region looks interesting. This looks like a landmark, right? And then the synthesis kicks over on the reduced region and like gets us the synthesized program. Right.
Interesting. Yeah. Have you experimented with any of that at all, or is that all future work?
No, that's like something we are doing currently. Right. Yeah. In this work, we haven't done that. Yes.
All right, great. I think I'm just going to double check. I think there are no more questions. So thank you again for the great talk. It's very kind of it's very cool that it works better with OCR than HTML. That's a neat little thing.